All right. Hello, everybody. Welcome. Welcome. This is Maintaining Code Quality at Scale. By me, I'm Jordan M. Adler. It's great to meet you all. Let's go ahead and talk about the agenda here. Just to give you kind of a quick idea of what we'll be talking about, I'm going to give you kind of a brief architectural overview of what a typical consumer SaaS software organization looks like. And then kind of talk a bit about the CISA quality model, which is kind of a method for a mental model for understanding quality of software. And then I have a mental model I've derived called the SaaS change pipeline, which is all about the process for modifying software that's being executed as a service, right? Talk about some of the KPIs. We'll go through the challenges in managing code quality at scale, what those challenges are, and then we'll kind of go through a cookbook of techniques that help optimize some of those KPIs, and hopefully, you'll walk away with some actionable items, but you also walk away with a better understanding and a couple mental models that you can use to better understand how to deal with code quality, code velocity in your organizations. We'll have some time for questions at the end as well. There's going to be a lot of straw polls, so I'm going to go ahead and start one now. Who here has a software architecture that looks roughly like this? So you have a big old backend, doesn't really matter. You have a kind of a clearly well-defined API, and then you have the decoupled code on the outside, the internet. So this is a pretty typical. So you have an Android, iOS web app, and maybe some third-party callers, but you have a very clear division between your front and back end. Are there folks like this? Yeah. So a case where that's not true is for typical MVC apps. This would not be true because your MVC monolith includes presentation information. You actually output HTML or some other sort of presentation media instead of outputting, kind of having programmatic access and decoupling in this way. But this is pretty typical, and there's of consumer SaaS organizations. And there's a couple things to note here, kind of in the bottom right in what I like to call Dunkin' Donuts color coding. We have release cadence, so how often we release something. And you can see kind of on Android and iOS, it's shrink-wrap software. You're delivering digital software digitally. You could theoretically put it on a disk and sell it in a store, but in practice, there are more streamlined approaches, and you install them via app stores, and these app stores have review processes. And so as a result of that, there's typically a bit of a delay, and it doesn't necessarily make sense to push updates too frequently because of the size of the update going down to users. And so most organizations tend to do biweekly in this space that I'm familiar with for those. On the back end, if you release as much as you want, it doesn't matter. You're always kind of running one version at a time. But on the Android and iOS side, you release every so often, but you kind of have these old versions running in perpetuity. So for example, you might have old Android apps running on old versions of Android in parts of the world where the phones may not be capable of running newer operating system with Android. And so that's just not available. It's a little less of an issue on the iOS ecosystem, but it still exists. So for example, one of the most common versions of iPad is iPad 2, and iPad 2 has a pretty large usage base still, even though it doesn't support the latest version of iOS. And so many apps that are targeting the latest version of iOS cannot be installed on the iPad 2. On the web side, things have changed. So as we've kind of transitioned more towards client-side driven web development with things like progressive web apps and single-page applications, there's often quite a bit of, there's a lot of decoupling going on between the back end and that front end, and having a clear delineation that's more in line with what mobile apps have. And so your web app essentially, unlike Android and iOS, when you deploy to your own server, your own CDN, and so you can kind of deploy whenever, and it updates more or less immediately. As soon as the user gets in touch with the server to rehydrate the data in the app, you can get a new version. So you don't have exactly one version running as you might on the back end, but you kind of have one plus whatever the last cache version that the user has, which is what executes first. And so there's a relationship here between release cadence, release longevity, and kind of quality constraints in the pipeline. So there's something to note there as well. Okay, so the CISA software quality model talks about characteristics of software quality that are concerns. So reliability is kind of chief amongst those. Does this do what I want it to do? Is it available? Is it defect-free? Efficiency talks a bit about the extent to which resources are required to execute the software. So in SaaS context, when you're not running, an application on someone's desktop, you're paying for CPU cycles. That's really important. And when you have, say, thousands and thousands of your application instance running, a small percentage change in resource utilization can have profound effects. So, there certainly are cases where you can save millions of dollars on an annual basis by, improving memory utilization by 20%. This is not unheard of. 20% is hard to do. And over time, you kind of have less low-hanging fruit to get to. So there's a sort of, depending on the technology stacks, a sort of local maxima. Security is also part of that, obviously. Maintainability is a huge part of quality too. You want to be able to have software that's adaptable, legible. Software that's stale and never changes is dead software, effectively. And so that's kind of something that's a key characteristic. The CISC model also includes size. Size is, thank you so much, size, I don't really think of as a significant concern. I think early on, size, in kind of the understanding of software quality, size was used as a sort of proxy for complexity, lines of code, function points, and it can be, but in reality, in my mind, size is just a part of maintainability. It's a part of efficiency. It's a part of reliability, too. And these things are important, right? So it's a little less, in my opinion, relevant to actual software quality, but this is part of the model. And when we look at how we actually change software that's running in production, I kind of try to think about it as being kind of an ongoing process, a pipeline, if you will, where you have hundreds of engineers all being targeted towards specific problems, and depending on their level of seniority or their level of experience or domain expertise, they might be given a different kind of problem to kind of solve and identify. And so part of that is defining the problem that you're working on. Maybe it's, we've noticed that users try to do X with our software, but they can't. Or we would like to improve the extent to which, people can, or we want to reduce the amount of memory utilization for this piece of software, right? That's a problem. And you have a clear problem statement that you're targeting against. And then you have the design phase where you take this kind of isolated problem statement with a clear scope, what's in, what's out. And if you don't have clear scopes, things can get out of hand really quickly. And so you take that problem statement, you identify potential solutions, you design something that makes sense. Typically, this coincides with implementation, prototype a little bit, hack it out, see what works, see what doesn't. Sometimes you have to get your hands dirty before you can figure out exactly what needs to be done. And in organizations like this, typically we produce a design document, and a design document can be used to collaborate together on a design to identify the optimal design for a particular problem statement. And then typically the solution implementation involves a delta, like a code change, a change review of some kind, and then that goes through a review process as well. So you have a design review and implementation review, and we'll talk about that a bit in depth. And then you deploy your change, you monitor your deploy, you make sure that your hypothesis or whatever it is you were attempting to change actually changed in the way you expected. You make sure to monitor usage and make sure that there's no errors or defects that you observe. And then the system is just an ongoing operation, right? It's as SaaS software, you're not delivering something shrink-wrapped that you don't have to worry about once it's shipped. You kind of are constantly executing and constantly operating the software. And in fact, in this model, a deprecation is effectively just reducing the size of the software being run in production. And so it's the same as this process. The kind of the waterfall, the SDLC model that we're used to seeing is very geared towards a waterfall approach towards and delivered software approach to engineering, which is not at all what I see in these large organizations, internet organizations today. So what are the kinds of things on this pipeline that are performance indicators, things that we want to optimize for? The first one, obviously, is the defect detection rate. How many bugs do we discover, and where do we discover them? So the earlier we discover a defect, the cheaper it is to fix. This is true in any sort of management, factory management, software management. The earlier you locate a defect, the cheaper it is to fix because less time has been invested in that approach. So for example, a faulty design that's already implemented and has maybe, I don't know, 5,000 lines of code and a commensurate amount of time invested in it is going to be more expensive to adjust than if you caught it at the design kind of review stage. So identifying the defects earlier are better. Making sure that you identify them before they get to production, always a good thing, right? You don't want users to be your beta testers, right? You think about the change size. So for example, if I have a diff that's large, that's a larger risk change, right? A large delta has more entropy, more risk, more change elements that when deployed could introduce issues into the system. We also think about the change throughput, how many changes are coming into the system. Ideally, if you have 100 engineers, and you have a certain amount of kind of work that they're able to produce through that system. You look at latency. So how quickly do we identify a problem and then are actually able to execute that problem, execute a solution against that problem and address it. Look at the number of change agents. So for example, change agents in this case being typically software engineers. How many software engineers are using the system? And then how much time are they allocating to it, right? So for example, a software engineer who spends half their time in meetings and it fragments their calendar is going to have a less effective approach towards problem solving, or it's going to have an impact on throughput and latency because of the extent to which they're unable to have kind of focused time to work. And legibility and predictability is important too. People need to understand the pipeline. They need to understand the process. When you have a prediction or some understanding of something and then it turns out that that's not the case, it's often measured in WTFs per minute, right? And so one thing kind of emergent property of all these characteristics is complexity as well. If you have, for example, 100 software engineers working on the same system, and then you go from, say, 100 to 200, you might expect to see twice as much throughput, but that may not actually be the case. And in fact, it often isn't. There's a kind of nonlinear growth to the number of software engineers working on something and the amount of throughput of change for that thing. One part of the challenge is humans. We unfortunately are organic machines. We are made of chemical processes, and sometimes they're geared towards things that are not exactly optimized for writing software. So one consideration is working memory, right? So how many things can you hold in your head at one time? Your ability to focus on something. These are biological things that impact our ability to code, and the way in which an organization influences those characteristics. So thinking about things like interrupts, right, can be problematic. Access to knowledge. So for example, I might have a level of expertise that I've invested in the Perl programming language that's not necessarily the case for someone else. And so they're going to be less effective, right? So we have kind of a slightly inconsistent level of distribution of knowledge. Another challenge, of course, is egos and territoriality. I mean, these are part of biological constructs in humans and all animals that we have to kind of go beyond to cooperate with each other. That can be very difficult to do. As an individual, to grow beyond these things is difficult. We have a number of cognitive biases, horn biases, halo biases, things that, confirmation biases, things that make it hard for us to truly see and understand reality because of the details of how our brain works. And there's also kind of a diverse set of things. Like no two humans are exactly the same. They can't be managed the same way. They can't allocate their time the same way. They each have their own optimal version of reality. And when you're trying to coordinate hundreds of people, all of them working on having slightly different global maximas for their productivity, it's hard to do that. But that also comes at an advantage. That diversity gives us perspective. It allows us to distribute knowledge in ways that is most efficient and effective for human brains. So there's value in that cognitive diversity and that work style diversity, but it's a challenge as well. Having lots of humans is more challenging. So when you have really large systems with hundreds of people working on it, any knowledge I have on a system is necessarily out of date. It's what I knew the last time I looked at it. A lot of stuff has changed since then. I don't know what that is. Communications can be difficult, so you think about how do people email each other, how do people talk to each other, what is the expectation of turnaround time, the number of stakeholders that you have. So for example, if you need to decide what to do about a particular piece of software, you have a number of, you have a decision to make. There are X possible changes we can make. Which one should we make? The number of stakeholders that you have, a higher number of stakeholders makes it more difficult to schedule meetings, makes it more difficult to reach consensus because you have to deal with all these different people. And then of course, interrupts is always a pain, and interrupting flow state can have serious impact on productivity. And of course, quality as a result, and kind of coordinating these people, aligning their goals, having everyone work together, even though we have slightly different perspectives, is difficult. Software itself is also hard. I like to think like software engineering is really hard compared to things like carpentry or woodworking or plumbing because like it's abstract, it's invisible. When I talk about timers and gauges and dials, it's kind of an abstract thing that I have to think about. But when you work at like a water factory or water plants, like there's a pipeline right there and you can see it and you can walk up to it. And being able to visualize it, I think humans are much better geared towards things that we can see and interact with our environment, whereas software, it's like, okay, you get 2 pages of Vim, that you get to see at one time and you have to kind of keep the rest in your head. It's difficult. And when you have lots of software working together in a large system, it becomes impossible to know all of it at the same time. It's just not possible. And also measuring it and understanding it is difficult too. So for example, you can't take a metric, a measurement, across the entire system. You take a sample of a measurement across the entire system and extrapolate. But that necessarily comes with some level of confidence that's lower than 100%. So the accuracy of your measurements is not exactly 100%. And so you have some stochastic processes and stochastic thinking that's required to really understand software at a distributed scale. Part of it is also distributed computing is just hard. Networks themselves are notoriously reliable. And stateful systems are just challenging. Keeping a couple gigabytes of data in memory on one machine is fairly easy. A couple, terabytes is a little harder, right? And so thinking about how you distribute these things and the challenges associated with distributing stateful systems can be very difficult in coordinating these things. System identity leads to challenges too, so in security context that can be difficult. So there are a number of techniques that we use to manage these challenges, that we use to kind of optimize these processes and optimize the pipeline. So one of these is design and code review. We talked a bit about that before. Essentially, it allows you to leverage distributed knowledge and distribute knowledge across the organization. So I may not know the optimal way to implement a ownership system across our entire system, but I might know the way for a local portion of it. Someone else might know a way for the other local portion of it, and someone else might know another. And together, kind of, we can collaborate on a design document and share it and make sure that we leverage everyone's knowledge, because it's distributed knowledge in these organizations, to collect that into an optimal approach. So it's taking the wisdom of the crowds of your own organization and leveraging that. So it's really key. And it also, just by having a design doc, it forces you to think about the problem from first principles, from first steps, and creating that process around that is crucial to ensuring that you have, frankly, a log of the decisions that are made, documentation about why a system was designed a certain way. These things are, like, design documents are crucial for business continuity as well. Code review is pretty typical. I think catching human errors is the key part of this. I think folks who are earlier in the career can benefit from learning quite a bit from code review as well. So it's a really good thing. It also acts as security control. So for example, if you have a constraint, hey, every piece of code must be reviewed, the likelihood of a malactor being able to, an employed malactor being able to change a system in a negative way is reduced. Does anyone use design or code reviews? So there's code reviews, show of hands, code reviews, your organization? Okay. Design reviews? Some? Okay, yeah. Design reviews are important, for sure. Multivariate experiments. So if you have a change that you're looking to make, we want to see an increase in email signups. Well, once you have kind of something that you're a goal, you can create a hypothesis and model and experiment in your code and kind of roll it out. Say, take a portion of traffic, show them a different treatment, and measure the impact to which it actually has on that user. So you can kind of understand the impact holistically. You can understand the impact before rolling out a feature, before you've invested a lot of time in it already. Do people here use multivariate experiments? No? Oh, it's a necessity. It is absolutely a necessity. And having a holdout group also allows for regression detection, which is important too. So in the future, for example, if you release a feature, but you have 0.001% of all users never see that feature, and then a bug gets introduced, but you have this toggle switch still in there, and you can see, oh, wait, this weird holdout group doesn't see the bug. That gives you a clue you can use to kind of go through the debugging troubleshooting process. It's really, really useful. Gradual deploys. People use gradual rollouts, gradual deploys. Okay. So gradual deploys, it's kind of a stochastic process for evaluating quality. So you maybe have a change or release to a piece of software. You convert, let's say you have a fleet of 1,000 servers. Maybe you convert 2 of them at a time, or let's say 10%, and then you measure between this 10% and this 90%, the rest of it, what is the difference in these characteristics? So how many 500s am I getting in the 90%? How many in the 10%? And are these sufficiently different enough to be able to say, oh, there might be an issue here, and you can automate that process and have rollbacks. Cool. Abstraction management. This one is really key, and it's kind of the most difficult thing to measure the impact of and frankly justify investment in, but it is often, in my experience, some of the most impactful things that you can do towards maintainability. So thinking about abstraction management, I think about what are the tools that we can give product engineers, the building blocks that they can use to be able to change the system as quickly as possible, as safely as possible. And how do you make it composable, reusable, modifiable with a minimal effort required, right? Those are important things. And how you structure your code is what enables that. And all abstractions produce duplication. It's an inevitability. At some layer, there's going to be duplication. You need to decide what layer that is and if that's a good thing or not. Another thing that's important is nouns. You're naming verbs, functions, systems, and making sure that a noun correctly conveys what it does, that it's concise and precise, enables a true abstraction. A true abstraction being something where you don't have to care about, you can treat it like a black box. You don't have to care how it works. Abstractions can often be leaky. So for example, if you open a file handle, you don't expect to have to think about things like inodes, but you might sometimes, right? You might have to. And so thinking about making sure your abstractions are as leak-proof as possible is important. Unit tests are also a key tool. Do people here use unit tests in your organization? Okay, that's a much better show of hands. I'm glad to see that. The secret of unit tests, I'm going to read this off the slide because I love it so much. The secret of unit tests is that you have to describe the solution twice, forcing you to change both implementations when you need to, and warning you when you unintentionally change one. That's the secret. That's really the secret of unit tests. It essentially is a way to notate something in 2 ways, a kind of declarative way and an iterative way, or not an iterative way, but a procedural way to say, okay, this is the code we actually execute. This is what it does. There's 2 versions of it here. And if I change this one, I also have to change this one. It makes sure that it's an intentional change. And it's absolutely crucial for refactoring, and a necessity for refactoring, and it's great for regression analysis as well. All right, here's the fun stuff. Automated tooling. So we can have static analysis tools. So in Perl, this would be typically something like PPI. You parse the code as a document itself and not necessarily execute or run, for example, in Perl, like begin blocks or code transformations or substitutions, things like that. And as you do automatic analysis based on this tooling. You can do linting, you can do type checking, compliance for architectural concerns, presence of common anti-patterns. So there's a lot of what I like to call foot guns, things in Perl and in other languages where they are not as easy as they may seem, and it's very easy to accidentally hurt yourself. And having tooling that as an organization you own, you curate to kind of identify when people have these issues and prevent them is crucial. Dynamic analysis tooling, so this is one where you actually run the software. So the distinction here is static analysis, you don't run the software, you look at the notation. Dynamic analysis, you run the software, so you can think PPI like a parser for static analysis. For dynamic analysis, you have to run it in Perl. So things that you can do here is looking at network connections. So when I run this piece of software, what are the network that it connects to? Is that what I expect, right? So that might be an analysis that I might conduct. Is the amount of network output being sent when I run, stimulate the software with this particular input what I would expect? Are there side effects that I would expect to see too? Load testing. So you might have a little system that you load test and isolate and be able to better understand from that perspective. Fuzzing is another one. So you can just give it random inputs, see what fails and see what doesn't. Oftentimes that's very helpful. And then secondly, automated programmatic introspection. So for example, memory sampling or profiling. I know of cases where we run, let's say, every 15 minutes we run a memory profiler on a portion of all machines in the fleet. And so we can build from that an understanding of how memory usage in production changes over time. And of course, there's a distinction between memory usage at startup, memory usage after 5 minutes, memory usage after 10 minutes, and kind of watching that growth and understanding that as a crucial portion of programmatic introspection, which gives you tooling to enable code quality constraints and feedback loops. Do people use automatic tooling here? Perl Critic, Perl Tidy, something? Yeah? Okay. Organizational constraints. So are you familiar with the reverse Conway maneuver? No? Are you familiar with Conway's law? Conway's law basically states that the communication structures of an organization will be mirrored in the architecture of the software that they produce. So if you have a compiler team and you divide it into 4 teams, you get a 4-pass compiler. If you get a compiler team and you divide it into 3 teams, you get a 3-pass compiler, right? So essentially, the reverse Conway maneuver is identifying the architecture of the software that you want to see, and then creating the organization, creating the teams in the structure that would best map that out. Thinking about the comms channels that people use, how do people communicate with each other? Typically in large organizations, if you think about like an org chart as a tree, going up and down communication is very easy. Side to side is hard, right? Talking to your cousins is harder than talking to your parents. It requires a little more thinking. It's the same kind of thing. And so kind of reducing that friction, creating comms channels to reduce that friction is important. I've seen cases like WIP limits, work in progress limits. The number of open projects a team is allowed to have is constrained, so as not to kind of overload them. Error budgets. If you have an SLA and you say, I will be available at this degree, you are not, like your time that you're able to allocate is constrained for other projects, for new features. So if you are not meeting your SLA, you don't get to work on new features. You get to work on bugs. Time management is another one. So at Pinterest, we have no meeting Wednesdays, which is great. I get a solid, uninterrupted blocks on Wednesdays. And because everyone does it, I don't have to worry about, I don't, declining meetings, right? Because it's an organizational constraint. It enables all of us to do it. And all of us, when we coordinate meetings with each other, know that this is kind of it's something that we don't do, right? Maximum physical sites per team is something I've seen as well. Co-locating people can really reduce the threshold of effort required to communicate. And so having cases where I know at Google, for example, there were limits to the amount of sites that a particular team is allowed to have. So how many offices can people work on for a particular team? How decentralized are they allowed to be? I've seen constraints around language of communication. Hey, we standardize on English, we standardize on Chinese, we standardize on German. This is more popular outside the US. In the US, it's less of a conversation, but it can be important to have a consistent language to ensure that people in the office can all kind of join in each other's conversations, overhear each other, and be a part of a group, right? You think also about nudge seniority curve. Yeah. So a team with lots of people who are too junior can be less productive than a team with lots of people who are kind of spread out, right? And a team where everyone is too senior can also be problematic depending on what the characteristics of each individual on that team are interested in. And so I've seen cases where, they'll have like a manager must be, at a certain level, and then, it has to be higher than all the people that report to them. And then the tech lead has to be roughly the same. Like sometimes there's rules around, what we expect to see a team make up from a seniority perspective in order to ensure that you have a right mix of folks to optimize for high quality software, but also maximize for resource utilization, right? If you have sending a compiler designer to work on, low-level bug fixes is not necessarily the best use of time, nor is it the best use of business continuity purposes, right? You want to get folks in, give them things that they can do and grow them, and nudge seniority curves. I was going to say forced, but that's not entirely true. Can help there. So organizational culture, we look at things like psychological safety. Are folks able to dissent? Say, no, I don't think that's a good approach, or here's another approach. Are folks able to come up with things that they're not 100% confident that it's the right approach? Are folks able to criticize each other's thoughts and ideas comfortably? That's important, and oftentimes organizations will leverage that component of the culture, psychological safety, to produce better software. There's a direct relationship here. Having norms, social, like corporate cultural values around communication and empathy and user focus also help reorient conversations towards these things in cases where they get out of hand. Inclusion and diversity efforts can be highly helpful. So, for example, a team of product designers where everyone is from, the same part of New York City is not going to be as effective in designing products for the United States as someone from a more diverse set of life experiences. Understanding that failure is a necessary path to success and having that be a part of your organizational culture is also key towards quality software, surprisingly. And having, I've seen cases where team building kind of helps create a sense of team cohesion, which enables people to work more smoothly together. Celebrating impact. When people do something meaningful and you put them on a stage and you say, hey, this person did something meaningful, it gives them a sense of recognition, but also signals to the entire organization, these are the kinds of things that we are looking for, right? So it's a way to influence decision-making and influence project allocation without having to be heavy-handed about it. Eating together has kind of a base psychological component of creating a sense of cohesion that many of these organizations employ. Team clothing. So we all kind of get a T-shirt or a sweatshirt. I have one here. I think I have every company I've ever worked at has given me a dozen of these. And there's value in having that. It's almost like not quite a uniform, but it gives you a sense of, hey, we're in this together. It's a very visual marker of we're on the same team. And deliberately developmental organizations. So these are cultures where people create a sense of, hey, feedback is a part of our life here. We want to help you be more productive. We want to help each other be better. And having that be a part of your culture enables you to provide constructive criticism towards people's software and enable them to be better software engineers as a result. There are also processes that you can use, right? So pre-mortems, post-mortems. So pre-mortem being, we're about to launch this thing. What are all the ways it could fail, right? Post-mortems be, we just launched this thing. What did we learn? Having good feedback loops. So, for example, if you have a post-mortem where every time you have an outage, we have to have a post-mortem, understand what went wrong, and bring that back into the project allocation, the planning for the next quarter of what projects we're going to do. That's important. Knowledge sharing. So do we have folks who have more experience in Python or some particular system in the organization? Are they able to share that knowledge out with each other? Having a widely distributed knowledge enables people to be more effective at the software they produce. Fire hose of information. So this is essentially if you have an organization that's an open communication internally, sometimes you can get to be too much communication, right? So too many monthly meetings, too many emails, too much of this, and that can be too much. So you have to think about Are we communicating to the correct number of people in the correct way at the correct level of detail? Distributed decision-making is kind of an organizational process that also leads to better software. If I am an architect up in my ivory tower and I write up UML diagrams and say, here you go, that's going to result in worse software than if I say, here's a problem. Please go figure out how to solve it and I'll help you, right? Design sprints is a process towards identifying what the, like a design of something. It's a way of reaching design by committee without having design by committee, right? So it addresses some of the errors in a typical design by committee process. And also just hiring, firing, and promotion, right? So if you have a team of software engineers and one of them is not pulling their weight, that degrades morale across the team, and that results in lower productivity. Simple as that. And when you hire, you have to be thoughtful about who are you hiring? What are the qualities and characteristics that we're hiring for? And sometimes that's that you unintentionally select for characteristics. You might accidentally be selecting for, because of your hiring process, people who are very extroverted. That doesn't necessarily result in better software, right? And so it's a very challenging thing to make sure that you do this correctly, but it's an important part of an organizational process towards arriving at good software. And firing is crucial too. If you have someone who's not performing well, or if they're making ineffective decisions, those decisions live forever, or until they're reversed, right? And so the longer you have someone in who's underperforming or having a negative impact in some way, the more damage they can do. Okay, service-oriented architectures. Monoliths, microservices is kind of like the extremes, angles of the spectrum. So on a monolith, you have one piece of software that does everything. On microservices, you have highly fine-grained services that do this. But all of these are part of a service-oriented architecture. And you need city planners, right? If you have devolved decision-making, distributed designing, you need someone to look at the big picture and holistically say, hey, this service graph is cyclical and results in highly inefficient communication. Or we put all our business logic over here, but all our systems over there, and the amount of communication between these two networks is higher than it needs to be. And so the latency for keep serving online requests is too high. So it's important to have constraints on your service and think about the ways in which your rules that you design your service-oriented architecture around have an impact on software quality. So for example, if you create constraints around valid solution spaces for particular problems, so I'll talk about that on the next slide. If you have operational constraints, for example, let's say languages, if you say, hey, we're only going to use these 5 languages unless there's a reasonable exception, having a rule like that reduces the complexity of operating these systems, right? So training your operators on what kinds of languages and introspection tooling, because they're all a little different. But it also reduces the solution space so that when you decide what language to use for your next project, it becomes a much smaller decision to make, right? And that's much easier to deal with as a team, right? So constraining the solution space for an engineering organization can result in higher quality software. And in this case, not just quality, but velocity, right? So the fewer choices you have to make, the quicker it is to choose one. Defining SLAs and SLOs at the correct level. If you say, hey, I want to be available 99.95% of the time, and you go over that, you're really kind of doing yourself a disservice, right? Because you're spending time on making your software more available than it needs to be. And you ought to be spending your time on making other parts of the system better. So making sure that you have SLAs at the correct level and that you're meeting those are important. And SLOs is kind of an objective. So an SLA is what you agree to. I agree to 99.95, but internally, for myself, I'm going to try and hit 99.96. And having those two things be decoupled can be important for effective commitment towards your SLA. I've seen organizations also have SRE acceptance review. So before you actually deploy some new piece of software, you have to have the design and the implementation reviewed by an SRE, someone who's focused on the operational concern, so that they can make sure that it meets their needs and give you pushback if you say, hey, you know what, I don't approve of this. You're using this system in a way that doesn't make sense. And having that process can nudge designs in ways that are more thoughtful about what SREs need. API-driven workflows is another technique. So having API specifications and making sure that people work against API. So for example, you have an Android team, an iOS team, a web team, and a backend team, and they all have to talk to each other to design the system. That's not good, right? It's better to have all of them design an API to begin with, and then all target that API. And not only does that make the process, reduces the amount of communication between these stakeholders necessary, which makes things move quicker. But it also kind of front loads a lot of the challenges in communicating. And also what it does is gives you cheaper integration testing, because you really only have to test against adherence to the API. You don't have to run these two systems against each other. Code formatting. Sorry about this, but the more consistent software is to read, right? Notation. So the code is essentially notation. The more consistent notation is, the easier it is to read. The lower cognitive effort is to read. So for example, if you have a standard set around saying no postfix operators, you can't say return unless, you say if not, then block return. And having that consistency means that people can read code better. Perl Tiny and Perl Critic give you some of this. There are much more opinionated code formatters out there. And this is one case I think other languages that have slightly different design philosophies enable them to be more successful. Security audits, this is having a domain expert inside of an organization. You cannot reasonably expect me to be a security expert in addition to all the other things that I do. It's not possible. But it is important to have a security expert come in and think about security, think about the specifics of this, and have tooling and processes that enable them to give you what you need to produce better quality software. I've seen folks try and train software engineers to think about quality, and that security, and that helps, but nothing beats someone whose full day it is, and a specialist. A security specialist will outperform a generalist with security training. And it's also important to have external audits. So a group of humans is necessarily going to miss things, and having a case where, having external parties come in and say, hey, you missed this thing is really important too. Taint tracking is another one. This is a feature inside of Perl itself. Other languages don't have that close, but essentially making sure you understand what user input is, tracking it, sanitizing it correctly is a technique that enables higher quality software. Reproducible production in lab environments, so having a hermetic reproducible production-like environment, say with Docker containers, and having people be able to up and quickly get a little mini version running in their dev environment is important. I've seen cases where compile time is on the order of days. That has a negative impact on quality and velocity. So it's also important to have various levels of isolation. It may not be practical in highly distributed systems to be able to fully isolate a piece of development software. But having the scope and breadth of production data is also important, right? So oftentimes, you might encounter a bug that only applies if you type into this particular text box with a language that you don't even know. That's going to be hard to reproduce. But if you have production data where you have that giant corpus of information that you can use, that can be crucial towards getting higher quality software. Yeah, so this is kind of a set of techniques that I've seen folks use to maintain code quality at scale. It's a challenging space and something I think is evolving, but there's a lot of research that goes into it, and I hope this has been helpful. And we have a few minutes for Q&A. Yes.
You mentioned the balance between velocity and quality, and you listed that under organizational culture.
Yeah, so the question was that I mentioned a balance between velocity and quality and added that under organizational culture. Could I expand on that a bit? At different levels of product maturity, at corporate maturity, it may not be important to care about the quality of your software, to be honest. Like if you're writing, having software that is high quality and you've invested a lot of time in making it defect free that you then delete next week because it turns out that was a bad business strategy, not a good use of time, right? So as you think about it, and organizations and in different levels of maturity have a different needs, balance. Like you can move very quickly if you don't care about quality, right? But you can also care about quality too much such that you're moving too slowly. So creating if you don't think about, the latency and the throughput of this process, and you just focus on defect location and defect rate, you're going to end up with a system that is highly stable and highly non-adaptable as a result, right? So if I have to go through, hours of committee review process to change anything, guess what? We're going to catch a lot of bugs, but we're going to change less frequently and thus be less of an adaptive organization. So there's kind of a balance to be made there. And that's often a cultural one, and it's one that has to change as an organization grows. Yeah.
I work on projects of about 2 people at most. In your experience, do you have any crossover between the production engineers and the development engineers? How much information about the design needs to go back and forth between the development and the production?
Yeah, this is an interesting question. So how do you kind of, what does the communication structure look like? What is the decision-making process and relationship between software engineers and development engineers and product engineers? In organizations I've been in, we use SWEs and SREs, so software engineers and site reliability engineers. And the exact shape of operations, I think, is an evolving part of our ecosystem now. So kind of the DevOps movement and making sure that we kind of automate as much of that as possible, and bringing more engineering skills into the system administration sector has been a part of, I think, the story of operators for the past few years, past decade perhaps. The exact relationship between these two things varies from organization to organization. In my experience, there needs to be someone who thinks about that, who's singularly responsible for operational concerns and what happens once the software engineer is done with the project, right? Someone has to own it. And making sure that that owner truly owns it and has not just the responsibility, but the power to truly own it is important. The exact way that models varies. I've seen cases, like I said, about SRE acceptance testing. I've also seen cases where it's kind of an optional process where SREs will review it if you want. That one has less teeth and is less effective and often results in lower concerns for quality, because the goal alignment is different. So an SRE team cares about reliability, but a particular feature team really only cares about that feature. They don't. Their mission scope is well defined in that space, and so it's important to make sure that there is the correct level of balance of power between these two, and what exactly that looks like is a variable. Yes. Yeah.
And as a mid-sized company in that range, one of the techniques that we use, rather than having acceptance reviews, we have our senior developers in the on-call rotation, and then they share part of that pain.
Yeah.
Fixing problems.
Yeah, I mean, I think the key there is goal alignment. And good feedback loops, making sure the individual who's responsible for making a change, or who is designated as being the person to make the change, is also the one who feels the pain when the change is needed. And what exactly that looks like varies. And the exact division of labor is going to change based on the size of a team, the size of an organization, the needs. So you can imagine a company like Amazon probably has a different number of SREs than a company like Microsoft, right? Or a company like Yelp, right? Or even an organization that's equally sized but has has a product, doesn't run their own data centers. So Snapchat, for example. We'll have time for one more question. Anyone have anything? Does anyone have a rambly question where they actually just want to make a statement? Because I'll do one of those. There we go. We got a taker.
So if you have an emphasis on quality versus speed, that's demoralizing as
It can be painful, certainly, to have very high quality standards, and the red tape can be difficult to deal with. But sometimes it's necessary. So think, for example, spaceships and missile defense systems. You know, you have a different level of tolerance for flexibility and adaptability. It certainly can be. Thank you so much. Thanks for coming. If you have any further questions, I'll be out in the hall. Cheers.